The C-SPAN networks bring you long-form public affairs programming from the nation's capital and are a public service of your television provider. C-SPAN, created by cable.
Of national attention, and in case we have forgotten, because we keep hearing that 2014 has been the warmest year on record, I asked the chair, you know what this is? It's a snowball, and that's just from outside here. So it's very, very cold out, very unseasonal. So here, Mr. President, catch this.
So let's set the politics aside for 1 second. Since the 1960s, we've had pretty solid evidence that humans are contributing to an increase in what we call greenhouse gases. And then we had pretty definitive evidence of that through the late 1970s and 80s. And so there's really no disagreement in the scientific community that human behaviors are leading to an increase in greenhouse gases, which lead to an increase in what we call climate change, or a change in our global climate due to human behaviors. Unfortunately, since the 80s, climate change has moved to become a political issue because people cannot agree on what to do with this information. How should we spend tax dollars to fight it, etc. And so you can see this brilliant tweet from our president. This was before he became president. This was in 2012. Stating that the concept of global warming was created by and for the Chinese in order to make U.S. manufacturing non-competitive. Obviously, this is nonsense, but I show it to you here not just to make you angry, but to point out just how divergent people's opinions are on climate change. And so we're not going to focus on politics with this lecture. I'd love to chat with you all about it, but our online forum doesn't really lend itself to that. So instead, I'll just focus on what you need to know to understand the basics of climate change, stuff that's probably already in your wheelhouse, and then we'll talk about the politics when we get back to school next year. So here we go. So let's start from the very beginning with the very basics. The greenhouse effect. What is the greenhouse effect? To put it very simply, the greenhouse effect is the idea that the Earth's atmosphere contains gases which can trap heat emitted by the sun and keep that heat within the atmosphere, so that the atmosphere then acts as sort of a blanket, which then keeps the Earth relatively warm and also relatively stable. So what's important to note is that the greenhouse effect, of course, is essential for life as we know it, because without greenhouse gases, when the Earth is facing away from the sun, it would be so cold that it would, things would freeze and life would not be possible. So what the greenhouse effect does is it allows a stable, slightly warmer temperature, well, I guess drastically warmer temperature on the planet, which then allows us to sustain life. So the greenhouse effect, of course, is a very good thing. What we're talking about today with climate change is what happens when this very thing that keeps us alive goes perhaps too far, when these greenhouse gases are in such a high concentration that the temperatures rise to unstable levels. And that's what we're going to discuss. So let's talk about how this occurs. So the first thing, without getting into too much physics, we're going to discuss how energy can travel in the form of waves. And so when the sun emits energy, it travels through space and eventually hits us on the planet Earth. And all of the energy coming in from the sun travels as waves. And we have to think about the amount of energy present in different types of waves. And so the one way to think about this, and the only one we'll focus on today, is what we call the wavelength. Or if you look right here, the wavelength is just the difference between peaks in these waves of energy. If you were to imagine sort of being hit by these waves, you'd have a wave striking you once here at this point, and then again at this point, and then again at this point. This is a longer wavelength. Down here we have a shorter wavelength where you're going to be repeated. This wave is repeated much more frequently, and we call this a wave with a higher frequency. So this energy has a higher frequency than this one because the lengths are shorter, so they would hit you more frequently, if you will. And the big picture here is that a longer wavelength energy source, or longer wavelength radiation, as we call it, will have less energy than shortwave radiation. And this is important when it comes to understanding how the greenhouse effect actually works. So the sun is sending all kinds of radiation toward the Earth, long waves, short waves, plenty of in between. And then as this radiation hits the Earth, some of it can get through the atmosphere and that warms us up, and some of that radiation gets reflected back out into space. And so the sun is going to be emitting all kinds of radiation, including shortwave radiation, and some of that shortwave radiation gets through the atmosphere and actually hits the Earth's surface. So in this diagram right here, what we're looking at is basically just a schematic of radiation coming in from the sun. What we're looking at here is shortwave radiation. Again, this is shortwave, therefore it has a high energy level. So this shortwave radiation comes in from the sun. Some of this is going to be reflected by the clouds, and then some of it is actually going to get through the atmosphere and actually hit the Earth and absorbed by solid surfaces on the Earth. Now, some surfaces are more reflective than others, and so they'll bounce that radiation right back out. However, other surfaces will absorb that energy, and when they absorb the energy, they warm up. And so this is what actually warms the surface of the Earth, this shortwave radiation getting absorbed here. Now, as the Earth starts to warm up, it is going to release that heat back out into the atmosphere. Now, when it releases that heat, it's a weaker, less energetic form of energy, so it's longer wavelengths. So we have short wavelengths coming in from the Earth, from the sun, warming the Earth, that heat bouncing off of the Earth, radiating back off of the Earth. That comes out as weaker, longer wavelengths, which then travel back out, and they attempt to move out, and some of that gets back out into space. But that heat, that long wavelength radiation, can get trapped in the atmosphere, and when it does, it gets trapped by basically hitting these greenhouse gases, which trap that long wavelength radiation, that heat, and keeps it within the atmosphere so that the Earth, overall, stays just a bit warmer. So the syllabus sums it up in this statement right here. The warmed Earth emits longer wavelength radiation. That's heat. So short wavelength radiation comes in from the sun, warms up the Earth. The warmed Earth emits longer wavelength radiation, which we call heat. That heat can get trapped in the atmosphere by greenhouse gases. Now, just to give you an idea of all the radiation coming in from the sun, we have shorter wavelengths down here, longer wavelengths over here. This is where our heat is located. This is the radiation emitted from the warmed Earth. This is all the shorter stuff, and then just a small little sliver of that is the light that we can actually detect with our human eyeballs. We call this the visible light spectrum. We also include some ultraviolet light in the shorter wavelength range, and then we have some infrared radiation here as well. The longer wavelengths are what we would detect as heat. Here's one more look at that diagram, put just slightly differently. Shorter wavelength radiation coming in. Here's our warmed Earth now re-emitting longer wavelength heat, longer wavelength radiation. And much of this is going to get trapped in our atmosphere, and a little bit of it will get through if there's a window in the atmosphere, if you will, that can go back out into space. But a good amount of that heat, that long wavelength radiation, does stick around because it gets trapped by greenhouse gases, and this is what causes the greenhouse effect, the trapping of longer wavelength radiation. I think I've said that enough times now. So let's focus now on our greenhouse gases, because greenhouse gases are basically any gas which can trap heat or long wavelength radiation. And so what are our primary greenhouse gases? Well, we have water vapor, which might be a surprising one, and carbon dioxide. Those are the primary greenhouse gases. We can also include methane on the list. And IB refers to the last category as oxides of nitrogen, there's basically different nitrous oxides, and so we have NO2, NO3. These collectively are the oxides of nitrogen. So those are our major greenhouse gases. Again, that would be water vapor, carbon dioxide, methane, and oxides of nitrogen. And the role that they play in the greenhouse effect is that what they do is they trap long wavelength radiation or heat, maintaining a stable temperature on the planet. by, again, here it is. Again, these are statements from the syllabus. That's why I'm putting them here in big bold letters. Greenhouse gases absorb long wave radiation, therefore they retain heat. Nice little schematic here of our greenhouse gases. We have our CO2. Water vapor is not on this diagram, but it is important. Don't forget water vapor. That is a greenhouse gas technically. So we have CO2, we have methane. CFCs are not really going to be considered a greenhouse gas here. They cause other issues with the ozone. So we're going to focus on CO2, methane, and oxides of nitrogen. And these guys are going to be trapping radiation emitted by the Earth, like this diagram shows here, making a nice warm blanket around the Earth. We call this the greenhouse effect. Now, without the greenhouse effect, temperatures would probably be quite dangerous, freezing, so we want this to occur. Now, let's take a second and consider why CO2 and H2O are such a problem when it comes to the greenhouse effect. Consider this. What we're looking at here is I know it's not a chemistry class, but just do it. We're looking at the reaction for combustion or metabolism, actually. So every time you burn something, here's what's occurring. You have some kind of fuel, some organic fuel. In this case, this is methane. If you light this fuel, you need a little bit of oxygen to keep the fire going. You guys know that, to let your fire breathe for it to burn. And when this occurs, when you burn your fuel in the presence of oxygen, the waste products that are released are CO2 and water, and those are primary greenhouse gases. So every time something is burned, we're releasing these two primary greenhouse gases. But guess what else is true? Every time your cells conduct the process of cell respiration, in other words, every time you turn your food into energy, every time we take glucose and oxygen to make some energy, we're going to be releasing CO2 and water as a waste product. So every living thing that does cell respiration releases CO2 and water, greenhouse gases. Every time something is burned, we're releasing CO2 and water, greenhouse gases. So when you think about the greenhouse effect, you have to consider all of the living organisms that conduct cell respiration and every fire that has ever been lit. And we consider water vapor and CO2 to be the most significant greenhouse gases for two reasons. One, they absorb a lot of heat radiated by the Earth. And then two, they're in high quantities in the atmosphere, relatively speaking. We're also going to include methane on the list of greenhouse gases, and it is significant for two reasons. One, it can trap some radiation, but two, when it combines with water, it can then form additional CO2 in the atmosphere. So it can lead to an increase of other greenhouse gases as it reacts with other molecules in the atmosphere. So methane is also an important greenhouse gas. Here's this slide one more time. I'm not sure why it's in here a third time, sorry. Moving on. And so if we're going to study trends in emissions of CO2, since CO2 is a primary greenhouse gas, what we have to do is try to establish long-term trends. And so the data that we will look at will track normalized trends, like before industry took off to the degree that we have today, and try and look at typical fluctuations in weather, yearly changes, to give us a general idea of what our climate is like. And then as we move forward to the closer to the present era, what we want to see is how far are we moving away from a normal baseline. And if you look at this general trend line, you can see our yearly values jump up and down because there's an increase and decrease in release of CO2 just due to seasonal fluctuation. We have more, we have an increase of photosynthesis in the hotter and wetter months, so that will cause a decrease in CO2. And so we have, seasonal fluctuation throughout the years. But overall, and then every few years, the CO2 levels go up and down, and there's plenty of fluctuation, and this is normal. However, if the overall trend starts to tick up higher and higher and higher, this is what we refer to as anthropogenic climate change, which is the idea that humans are causing the release of more CO2, which then leads to an increase in climate change. So an increase in overall temperatures globally, which causes a fluctuation in climate. Now, I said the word fluctuation, so I was referring to a fluctuation in climate. And this is important. When I was younger, we used the word global warming, and now scientists are urging a shift toward the phrase climate change rather than global warming. And the reason for that comes back to this video that I started with this guy by the name of Jim Inhofe. He's one of the leading climate skeptics in the Senate, or was anyway, or Congress. I'm sorry if he's a... Anyway. The point I wanted to get to was that climate change means that there's going to be an increase in fluctuation. So we're going to have hotter months and we're going to have colder months. The extremes are going to become more pronounced. And the reason for that is that as the temperatures around the globe increase, that causes some areas of the planet to experience obviously hotter summers, but then in other areas at the same time, due to shifts in the way that air streams will move through around the planet, that can cause actually colder winters at the same time in some regions. And so what we're going to see is an increase in extremes. So we're going to have wetter places, we're going to have drier regions, we're going to have hotter regions, we're going to have colder regions. And so when skeptics point to a snowball in an abnormally cold fall day, what they're missing is that climate change involves more extremes, not strictly an increase in temperatures every day forever. They're oversimplifying the science here. So we're going to move into a very specific example of the effects of climate change now, because we have to understand that as temperatures increase, it's not just that the planet gets warmer, but environments are going to shift as well. And we're going to focus for a while on just the effects on coral reefs. And perhaps you've heard of this. It's the phenomenon called coral bleaching. And this is important. It is in the syllabus. You have to understand how coral bleaching can work. So first of all, think back to the lesson from a few weeks ago about carbon cycling. What happens to CO2 when it's dissolved in water? Well, if you've forgotten, when CO2 is dissolved in water in high amounts, it can combine with other substances in the water and form a compound called carbonic acid. And so the oceans around the world are getting just slightly warmer and just slightly more acidic. So ocean acidification tied with a warming ocean is basically making this habitat unlivable for some corals. And this is why. What we're looking at here, and if you have a healthy coral, the living organism is actually not really what you're looking at. We're looking at the limestone or the rock formation, the calcium carbonate formations that the living things make. The actual animal that builds the coral reef is teeny tiny. They look like this. I'm going to move myself out of the way. So this little, well, it looks a bit like a sea anemone. It's called a coral polyp. And these are the animals that actually build our coral reefs. Now, when they're building the reef, they rely on a symbiotic relationship with these little brownish, greenish fellas. This is a type of algae called zooxanthellae. I believe I have that. Oh, no, I don't. I don't have it spelled out. Here it is. Zooxanthellae. You can pause and rewind if you need to. Zooxanthellae. Important to note. The name of these little algae. These are the zooxanthellae. And they have a symbiotic relationship with the coral polyps. And what that means is that they need each other to survive. The animals, the coral polyps, rely on the algae for some bonus nutrition, and the algae, the zooxanthellae, rely on the polyps for a home. And these are the organisms that are most sensitive to very slight changes in pH and temperature. And when they get upset by a change in pH or temperature, they will leave the polyp. And they go out and they swim in the water, and they look like this when they're free floating. And they'll basically attempt to try to find a new home, except they will not find a more hospitable place wherever they go because the entire ocean has changed. And so they will go attempt in vain to find a suitable place to live, and then in their search they'll die. And when they leave, the coral polyps will also die, and what's left is what looks like death and destruction. Bear in mind, this was always dead. This is the rock formation that was built by the animal. When the animals leave, the corals look bleached. They look dead, and this is what we call coral bleaching. We see a stark increase in coral bleaching worldwide right now due to increases in temperature and decreases in pH, more acidification. This is all because of an increase in CO2 emissions. It's all related to anthropogenic climate change. So there are many examples of how climate change is affecting humans and ecosystems around the globe. Sneeze. However, the one example that you need to know for IB exams next year is the zooxanthellae and their relationship with coral polyps, and how life is not possible for these corals thanks to climate change. All right, so just to wrap things up, here's a quick exam question just to review. Of course, this is just one question. Don't forget to read the textbook and flesh out your notes. But here's our review question. So, for 4 marks, outline how greenhouse gases interact with radiation and contribute to global warming. So I'm going to click pause. You'll be tempted to just keep watching, get the answer. I highly recommend that you pause your video now. Or now. How about now? Pause your video. Try to get to 4 marks on your own. Really think of 4 things. And I'll bring you the mark scheme in just a second. So again, pause your video right now. Okay, and here is the mark scheme. So you get a mark for saying that CO2 is a greenhouse gas. Woohoo! You get another mark, up to 2 marks already, for stating any other greenhouse gas, like methane, nitrogen oxide, or water vapor. You get a mark. Letter C, sunlight, light, solar radiation passes through the atmosphere to reach the Earth's surface. It's too easy. D says CO2 in the atmosphere or greenhouse gases absorb, trap, reflect back radiation. Too easy. This really should have been like 6 or 7 marks, because you should also point out, like letter F says, that solar radiation is mostly shortwave and that the heat emitted is mostly long wave. So you really should have said those things. I hope you did. As usual, you can get marks for a clearly annotated diagram, if you're into that kind of thing. And then this mark I skipped over right here, CO2 in the atmosphere, greenhouse gases allow shortwave radiation to pass through the atmosphere, but absorb long-wave infrared radiation. So that kind of sums all the other marks up. Hopefully you could have gotten to 4 marks. It's pretty simple, just to double down and emphasize the difference between shortwave and long-wave radiation. That's pretty essential here. So that's what IB wants you to know about climate change and the greenhouse effect. Pretty simple stuff, I think. So go ahead and wrap up your 4.4 notes. Don't forget to go back and finish up your complete study guide for all of topic 4. You will have that review test as soon as we get back next year, hopefully in person. But it's up to you at this point to go back through the lessons and the reading and make sure you have a complete study guide with understandings, applications, and skills identified for all of topic 4. Good luck, and that's all. Ta-ta.